Okay, so I'm going to cover rationalizing the denominator. And this is an important skill when you're doing anything with radicals, and you might have to like solve an equation with radicals, or sometimes you just get radicals in the denominator. So let's just start with the definition of the nth root. So you know that square roots are reversing the squaring process, and so that's working with exponents of 2. And we can reverse other exponents, and that's by taking what is called the nth root. So the definition is that b is an nth root of a if b to the n is equal to a. And so it basically undoes the nth root will undo whatever exponent n is. And so we use the same symbol, but we have a little number kind of above the little v part, indicating what root it is. So that is called the index, that number. It's, if you don't see the number, you assume it's a square root index 2. The thing inside the radical or under the radical is called the radicand, and then the whole thing is called the radical, or just that symbol is called the radical. So there are some rules for simplifying that we use. If you have an nth root of a to the n, as long as the n is odd, you just get whatever is underneath the exponent. If n is even, if there's a negative under the exponent, like if it's in parentheses with the negative, you take the absolute value, get a positive. We have what is also the product and quotient properties or rules, where when you multiply radicals, you can combine them under a single radical. This also works in reverse. And if you've got two radicals divided, you can combine those in a single radical with a fraction on the inside. Again, that works in reverse, and so we'll be using some of these properties. So let's start with rationalizing the denominator, and this is also part of dividing radicals. So when we divide radicals, if you have a radical divided by a radical, sometimes your final answer ends up having, or when after you go through all the simplifying, you have a radical in your denominator. And we don't like to leave it in that form. We prefer to have radicals in the numerator. It's just easier to work with. So the process to get rid of those radicals in the denominator is called rationalizing the denominator. And it's called that because when a radical is in the denominator, when you take roots of things, you often end up with irrational numbers. So by getting it outside of the denominator, and usually it ends up on top, then now the denominator is rational. So that's why it's called rationalizing the denominator. So there are two basic cases we consider. If there's one term in the denominator, or if there's two. If there's more than two terms, it often can be simplified to down to one term or two terms. So that's why we only really consider those two terms, or two cases. So we're going to start with one term. So if you have one thing in the denominator, this is actually probably harder than if you have two terms, you are multiplying your radical, your expression, the fraction part, by 1. So you're multiplying the top and the bottom by the same thing. And you're doing it in such a way that you get the denominator radical to cancel out. So you're usually multiplying by a radical on the top and the bottom, but it may have different exponents on the inside than what you originally had, depending on what type of root it is. If it's a square root, it's easy. You just multiply by the same thing that you see, because the square root times the square root, those cancel out. But if it's like a cubed root or any index higher than that, you have to get a little creative. You have to kind of think about what you're trying to do. And so for a cubed root, for example, if you have the cubed root of a, in order to get the cubed root to cancel, you need an exponent of 3. So you have to multiply it by the cubed root of a squared, so that when you combine those, you now have an exponent of 3. And it goes the other way. So if you have something that's a squared on the inside, you have to multiply it by a to get it to have an exponent of 3, so you can cancel out. So it does require some thinking to know what you're multiplying by. So if it's like a fourth root, you need to have the exponent be 4 on the inside. Fifth root has to be 5, and so on. So we'll start with simple square root examples, and then we'll just kind of work up from there. Here it says rationalize the denominator and simplify. So you may also see just simplify, and it means the same thing, as you don't want your final form can't have that radical in the denominator. So we've got 1 over the square root of 7. So we need to get rid of the square root in the denominator. So if it's a square root, you multiply the top and the bottom by that denominator, by the same thing. So I can get my pen to work. I have 1 over the square root of 7, and I'm going to multiply by the square root of 7 on the top and the bottom. So when you multiply those, 1 times the square root of 7, you just end up with the square root of 7. In the denominator, the square root of 7 times square root of 7, that is the square root of 7 squared, or you can do 7 times 7, which is 49. And that square root and the square cancels. That's why we're doing this. And so you end up with the square root of 7 over 7. And that is rationalized and simplified because we can't cancel anything out. So often what happens is if you have a square root of the denominator, it ends up on top and then things kind of cancel out. So same thing with 9 over the square root of 3t. So we multiply by the square root of 3t on the top and the bottom. And so we end up with 9 times the square root of 3t, because we can't do anything there. And then in the denominator, we have 3t squared, or if you multiplied it, you would have 9t squared. That square root and the square cancel, and so we get 9 times the square root of 3t over 3t. Now notice that this actually simplifies, because we have 9 and then 3, we can do 9 divided by 3, which is 3. So this simplifies to 3 times the square root of 3t over t. So sometimes after you do the rationalizing, you can actually simplify after that and cancel some things out. So here are some new examples. We have the cubed root of b cubed over 3. So this is where we're going to use the quotient property to split it up into 2 separate radicals, and then we are going to rationalize, because we don't like to have fractions inside a radical. That's another thing, just conventionally we don't do that. So we're going to split it up. So we have b cubed over 3 inside the square root, so this becomes the square root of b cubed over the square root of 3. Now, the square root of b cubed, we can actually simplify that further, because that is, we can split that up as b squared times b. And then the square root of b squared is b. So that's going to be b times the square root of b over square root of 3. So all I've done so far is use the quotient rule and then simplify. But I still have this radical in the denominator that I need to rationalize. Now, I could have waited to simplify after I rationalize the denominator. Order doesn't really matter. I just tend to simplify first and then rationalize, and then if I need to, simplify further. And I do that just because sometimes it's quicker. Sometimes it's not. So my next line, I'm going to do the rationalizing part. So first I simplify. Now I'm going to rationalize by multiplying the top and the bottom by the square root of 3. Now, I can multiply, I'm going to use the product rule in reverse and combine my 2 radicals, the square root of b and the square root of 3. And so that's going to give me b times the square root of 3b. And then in the denominator, the square root of 3 times the square root of 3, that's the square root of 3 squared, which then gives us b times the square root of 3b over 3, because the square root cancels out the square. And then we can't simplify from there. So that is your final answer. So it doesn't look as nice, but that is considered simplified. I mean, we at least got rid of some exponents on the inside. We don't have a fraction inside the radical anymore. So now let's look at the one on the right here. We've got 2 over the square root of 48. So simplifying so we could just multiply the top and the bottom by the square root of 48, and then we're going to have to simplify the square root of 48. So since we have to simplify it anyway, I do that first. Just like in the previous example, I simplified the b cubed first before I did anything else. So I need to make a factor tree for the 48 so I know how that becomes with the prime factorization, and then I can simplify. So 48 I know is 6 times 8, and 6 is 2 times 3, and I know that 8 is actually 2 cubed, so I'm going to just write it like that. So we end up with 2 over, and instead of 48, I've got 4 2's, so that's 2 to the 4th times 3. So I've done the prime factorization of 48, and this allows me to simplify. So the square root of 2 to the 4th, now when you're doing a square root, even exponent, it divides the exponent by 2. So 4 divided by 2 is 2. So this is going to give us 2 over 2 squared times the square root of 3. And I can actually cancel out one of the 2's because I have a 2 on top and a 2 on the bottom. And so this will give me 1 over 2 square root of 3. So that's what it is simplified. And if this part is too fast for you, you can go review a video for simplifying, how to simplify these things. So now that I've simplified, now I see what I need to rationalize. I need to get rid of the square root of 3. It's okay to have a 2 down there, so I'm not going to do anything with the 2. In order to rationalize this, we're only going to multiply by the square root of 3 because that's what we need to get rid of. So I'm going to multiply the top and the bottom by the square root of 3. If you multiply by 2 times the square root of 3, you will end up having to reduce again. You'll basically undo that reducing that I did earlier. So it doesn't harm you, it's just extra work. So this gives me the square root of 3 on top, and then I get 2 times the square root of 3 squared. And the square root of 3 squared, that cancels, you get 3, so we end up with square root of 3 over 2 times 3, and then you multiply, you get square root of 3 over 6. Okay, had to stop the recording because the surgeon called about my dog. I don't remember where I was off, but it looks like I finished that problem. Okay, moving on to these examples. So those were all square root examples. Now I'm going to do a couple, some with cubed roots and that sort of thing, because they are different than the square root. So we've got 2 over the cubed root of 7. And in order to cancel out a cubed root, you have to have an exponent of 3. And so we need to multiply by a 7 squared so that I have a total of 3 7s there, so I can cancel out that exponent. So we have 2 over the cubed root of 7. And then we're going to be multiplying by the cubed root of 7 squared on the top and the bottom, so that we have 3 7s there. And so that will give us 2 times the cubed root of 7 squared over the cubed root of 7 cubed. And then the cube roots will cancel out, so we have just 7 in the denominator. And then normally if we have a number like 7 squared, we will actually square that number. So our final answer will be 2 times the cubed root of 49 all over 7. Now, next one here, we have negative 2 over the 5th root of y. So that negative in the middle, you can put it on the top. That's completely fine. Sometimes that's easier. So we have the 5th root of y. So we need to get an exponent of 5 in order to cancel out a 5th root. So I have 1y. So I need to multiply by 4 of them to get 5 total. So we are multiplying by the 5th root of y to the 4th, 5th root of y to the 4th. And so that will give us negative 2, oh, oops, make sure I'm in the correct color, negative 2 times the 5th root of y to the 4th, which doesn't simplify. And then we get the 5th root of y to the 5th. And then the 5th root and the y to the 5th cancel. And so we have negative 2 over the 5th root of y to the 4th over y. Okay, a few more here. So we've got cubed root of 5 over z squared. So when you've got a fraction inside the radical, you want to split it up first. So we're going to have the cube root of 5, this is using that quotient rule, over the cubed root of z squared. And now we want to have z cubed in the denominator. So I've got 2 of them. I just need to multiply by 1 of them in this case. So I'm going to be multiplying by the cubed root of z on the top and the bottom. So on the top I can combine those using the product rule to make one single cubed root, which is 5z. And in the denominator, we get the cube root of z cubed, and that z cubed, the cube and the 3 cancel, and so we're left with just a z in the denominator. So this gives us, kind of running out of room here, cube root of 5z over z. And it doesn't simplify further. That z does not really look like a z on the top. Okay, now this next one on the right takes a little bit more thinking. So I have 6 over the cubed root of 3y squared. So we need to get the 3 to cancel out, so we need the 3 to have an exponent of 3. So that means when I multiply, it's going to be a cube root. I'm going to have a 3 squared, because I need to have that 3 to get to a cube. But the y squared needs to get up to a cube as well, so I have 2 of them, I need a single y. So I'm not using the same, oops, I wrote the wrong exponent here. Notice that we're not multiplying by the same exponents. We have to choose our exponent based off of what we have and what we need to cancel out the cubed root. So this is where your critical thinking really comes into play. So on the top, I have 6 times the cubed root of, and the 3 squared is 9, so I'm going to just write 9y. In the denominator, we have the cubed root of 3 cubed y cubed. And so now that cubed root cancels out the cube, so we have 6 times the cubed root of 9y over 3y. And the 6 can be divided by 3, which will give us 2. So this becomes 2 times the cubed root of 9y over y. And so that is simplified. So that's one term, and that's actually harder than 2 terms, which I'm going to do next. So when you have 2 terms in the denominator, what we end up doing is multiplying by the conjugate. Now, it's easier in that there's less critical thinking, less thinking on what to multiply by. It's kind of obvious. It's a little harder though because you do have to FOIL. So that can be a little harder foiling with radicals, but you're multiplying by the same thing but with an opposite sign, and that will give you conjugates that when you multiply out becomes a square or a difference of squares, which is, one of the special things that we've talked about with factoring and multiplying polynomials. So the conjugate is just the same thing, opposite in sign, and then when you multiply it, you get a difference of squares. What happens is that the middle term, which will end up having the radical part, will cancel out, and then the other things that are squared have radicals, and that will cancel out. If you have two terms and it's a cubed root, it's more difficult, but we're not giving any of those to you in this course. You're only going to see things with two terms with square roots, because when you've got cubed root, it's a lot more complicated, and honestly, I don't think I've ever had to do that with a cubed root in the denominator. So no point in telling you how to do that. It's just with two terms, and it's going to be a square root. So we'll start with the left. We've got 6 over 4 minus the square root of 3. So the conjugate is of the denominator. So we have 4 minus the square root of 3, you multiply by 4 plus the square root of 3. And you do this on the top and the bottom. So that's the conjugate. And so we do need to distribute on the top. So 6 times 4 is 24, and then 6 times the square root of 3 is going to be 6 times the square root of 3. In the denominator, this is a difference of squares, or not difference of squares. These are conjugates, and when you multiply it, the 4's get squared, and then the square root of 3's get squared. That's where my brain was thinking difference of squares, because, well, that is a difference of squares. My brain today is not 100%, but when you multiply, you get 4 times 4. When you go through FOIL, that's 16. You get a 4 times the square root of 3. And then you get that minus square root of 3 times 4, so that's a minus 4 square root of 3. And then when you multiply, you get a negative square root of 3 squared. So you can see the middle terms cancel out. 4 square root of 3 minus 4 square root of 3 is 0. And then the square root of 3, when you square that, that cancels out the square, and you're going to get just 3. So you end up with 24 plus 6 square root of 3 over 16 plus 3. And so then you just add 24 plus 6 times the square root of 3 over 19. And if you could reduce, you would. If you could cancel something out, you would. Sometimes it might be best to wait to distribute on the top until after you've done the denominator to see if there's something that can cancel out. But 19 is a prime number, so there's nothing we can reduce here. So that is how we leave our answer. We'll leave it as a single fraction like that. Sometimes you can split it up into 2 separate fractions, 24 over 19, 6 square root of 3 over 19. And what you're seeing here is very common to how you'll see your output for like the quadratic formula when you start solving quadratic equations, which is one reason why you're kind of working with radicals, as we're kind of leading to that point. So let's look at the second one here. We've got negative 12 over square root of 5 minus 3. So I'm going to just stick the negative with the 12. It's just easier. And then we have square root of 5 minus 3. So the conjugate in this case is square root of 5 plus 3. And I always put parentheses to remind myself that we are foiling here. And maybe this time I will just wait to distribute the 12 until after I've taken care of the denominator, just to see if things simplify. It might make it easier. So, since I'm going to wait on the numerator for now, I'll just copy that down. To save yourself some work, you really want to recognize this will become a difference of squares. So we have the square root of 5 times the square root of 5. Those cancel, which will just give you 5. And then you have minus 3 times 3, which is going to be minus 9. So it really is worth memorizing a plus b times a minus b equals a squared minus b squared, because it will save you an entire step on the FOIL process to just know that that's how it's going to end up, and makes it slightly faster. So 5 minus 9, so I'm going to have, let's see, negative 12 times the square root of 5 plus 3, and 5 minus 9 is negative 4. So in this case, it was actually good that I waited to multiply the negative 12, because things will cancel. So first off, the negatives can cancel. The negative on top, negative on the bottom, they cancel. And I can divide the 12 by 4, which gives us 3. And so this would be 3 times, in parentheses, square root of 5 plus 3. And then I can multiply that out and get 3 times the square root of 5 plus 9 as the final answer, which looks much simpler than what's on the original problem where you've got this radical in the denominator, because now we don't have a fraction at all. So it did get simpler. Okay, square root of 7 over square root of 3 plus 2. So I've got square root of 7 over square root of 3 plus 2. So we're going to multiply by the conjugate, which would be the square root of 3 minus 2. And if I've got a square root of 7 in front of parentheses, I definitely want to distribute, because it's not likely to simplify. We don't normally cancel out square roots. So I'm definitely going to distribute the numerator here. So square root of 7 times the square root of 3 is square root of 21, which doesn't simplify because 7 and 3 are prime numbers. And then it's going to be minus 2 times the square root of 7. Then in the denominator, again, remember that the middles are going to cancel. So we're going to do the F and the L part only, because O and I cancel when you FOIL when it's in this particular form. So square root of 3 times square root of 3 is 3, because it's going to be square root of 3 squared. And then 2 times negative 2 is 4, so that's going to be a minus 4. And so that gives us square root of 21 minus 2 times the square root of 7 over negative 1. And then what that does is just change all the signs, because we're dividing everything by negative. So that becomes a negative square root of 21 plus 2 times the square root of 7. And we'll just leave it as that. Now, on the right we have negative 1 over square root of p plus square root of q. So negative 1 over square root of p plus square root of q. So the conjugate is going to be the square root of p minus the square root of q. And so if all I'm doing is multiply by negative 1, I could just distribute that through. I am also not, I can tell because the denominator doesn't have any numbers that nothing's going to reduce, so it doesn't harm us to distribute the numerator. So that's going to be negative 1 times the square root of p plus the square root of q, or you can just say negative square root of p, plus square root of q if you want. And then we're going to multiply f and l only because that's the special form here. So square root of p times square root of p is p. And then square root of q times square root of q is q, and because it's plus times a negative, it's a minus, so it's going to be p minus q. And there's nothing to reduce here. There's nothing that we can do. That's all we can do. So that is the rationalized form. That's this simplified form following our rules that we have. So now this is my last one, and this one's going to be a little bit more work because we have more things to multiply out here. So we've got radicals on the top and the bottom, and we don't care about the numerator being rationalized. We only care about the denominator. So I've got the square root of w plus 2 over 9 minus the square root of w. And we're going to multiply by 9 plus square root of w. And we're going to have to do that on the top as well. We are going to have to FOIL. So when I go through the FOIL process, I have, and on the top, I'm going to have to actually show some work here. Square root of w times 9. So it's going to be 9 times the square root of w. And then the outsides, actually, so we did the first term. And now outside is square root of w times square root of w. So I'm going to just actually write out what that is, square root of w squared. Or square root of w squared with the square on the outside, it doesn't really matter. Inside is 2 times 9, so that's 18. And then the last term's 2 times the square root of w. So because it's not one of the special forms, that's why I'm actually writing down out everything, because it's not a special form, so it isn't, I can't really do it mentally easily, so I'm going to write everything out there. Now, the denominator is the special form. That's why we're doing it this way. So I only need to multiply the f and the l. So 9 times 9 is 81. And then the square root of w times square root of w is w when those cancel out. So it's going to be 81 minus w in the denominator. If we really want, because I FOILed out everything on top, we can do the bottom as well. So that would be plus 9 square root of w minus 9 square root of w minus square root of w squared. Like, since we already did it on top, might as well do it in the denominator. So simplifying, I can add my 9w or square root of w and the 2 square root of w. So 9 plus 2 is 11, so it's going to be 11 square root of w. And then the square root of w squared just is going to be w. And then I have my plus 18. In the numerator, the middle terms are going to cancel. So I'm going to have 81, and then that's that minus w that I said that I had. And that's our answer. We can't cancel things out from here. We have a w on top and the w in the denominator, but they're added, subtracted. They're not multiplied, so we can't cancel out. That's what I call illegal algebra. I can divide a 9 out of the 18 and the 81, but not the 11, so I can't cancel anything out there. On the top, I can't reduce, or I can't combine any like terms there. They're all different terms. So that's our answer. That's as far as we can go. It looks kind of gross, but the key is that our denominator is no longer having a radical in there. So it's totally fine if we have one on the top. It's totally fine that we got more than 2 terms. We just want to make sure we don't have a radical in the denominator. So hopefully this is helpful. If I went too fast here, of course you can pause, rewind, and sorry about having to cancel the live. I don't know. I didn't want to have to get a phone call during the live and then have to be like, look, we have to go get our dog. I mean, I got one in the middle just recording here. So I just thought it'd be easier to, at least when I have time, pre-record versus having to leave live because I don't know what's going on. So hopefully this is helpful. And let me know if you guys have questions.